Alright, so in this video we're going to take a look at the concept of the induction machine. Now, this is not a introduction to the induction machine, rather it is a summary of the induction machine. So if you are not familiar with the properties of the induction machine, perhaps it would be wise to go back and review its operating principles, because the discussion here will be fairly superficial, and then we'll jump into some equations and look for a circuit model, but the actual physics of the machine will probably not be discussed here in a great amount of detail. Now, the induction machine is a mature technology. There are two main types of induction machine. One they call squirrel cage, and the other one they call wound rotor, which is also sometimes called doubly fed. And the control is difficult in the induction machine because the flux and the torque are coupled, unlike in the DC machine, which we've seen previously. So here, you see a figure, and this figure is a simplified diagram, and again, this is not a physics approach to it, but essentially you have, these are windings, so every one of these black bars you see here, so this is a winding, these are all different windings, and by windings I mean literally windings of wire. And so you would connect them to a three-phase circuit. For instance, you would connect a circuit like I don't know, one there, or wherever you would, let's say here, going off like this and off like this, and then this would also be connected to something else potentially, maybe not, depending on which type of machine it is, and so on. There's a gap between the rotor and the stator, of course, otherwise things would look messy. But we have some assumptions that we make here. The assumptions are that the air gap is uniform, the magnetic material is perfect, so there's no magnetic saturation, meaning the permeability is infinite. The flux density is radial in the air gap, meaning it goes outwards, like that, in the air gap. And we also assume that the flux density at any point in the air gap, due to any one winding, is a sinusoidal function of the angular position. Now, that's a lot of jargon and such, but these are simplifications and assumptions we're making so that the analysis we make later on is actually valid. And the last assumption is that all of these windings are identical. Now, if we can establish that that is true, then we can write the following equation. So we have lambda s is equal to ls is plus lm e to the positive j theta r I r. Now, these vectors that I'm drawing or writing, these represent space phasors. So this is a space phasor. So this is a vector, but this is a vector that rotates in space. Well, I guess this is not a space phasor, this is just a phasor, and then the three of them together would make a space phasor. So this is a phasor vector. And you have the other one, so that's for the stator flux linkage. Then you have for the rotor flux linkage, you have Lm e to the minus j theta r is plus Lr ir. And I will label these equations 1 and 2 because we're going to be dealing with a lot of equations here. So what's what? Ls is the stator. So this is the, sorry, that's Lm. Let's talk about that then. This is called the magnetization, or magnetizing. Let's call it magnetizing inductance. This is the stator winding inductance. This is obviously the same magnetizing one, and this is the rotor winding inductance. And these are the stator and the rotor flux linkages, basically. So I guess we can call them space phasors because, I mean, they are rotating in space, so we can say that these two, let's go back to our initial thing. So these two are space phasors of flux linkage. So the flux that is linked is obviously the flux in the rotor and in the stator. So, I mean, I think that goes without saying. Now, what is a space phasor? That I referred to this word a couple of times, and you may or may not have heard it. But a space phasor is essentially any three functions. So you can have three time varying functions. Let's say f, a, b, f, a, f, b, f, c. And so if f, a plus FB plus FC. Well, these are all functions of time. Maybe we can be a bit more accurate and write them as functions of time. So if FA is a function of time plus FB is a function of time plus FC is a function of time equals 0. So if they satisfy, space phasors satisfy these conditions. If this is true, you can then write a space phasor. So the space phasor is a function, or is a group of functions, I should say, is a group of functions that satisfy that condition, and if they satisfy that condition, you can write them as follows. So it becomes a vector, basically, and the vector, again, this is a mathematical definition. This is not a concept that's unique to flux linkages or induction machines. This is a general concept, and this is similar to the idea of three-phase voltages and such. So you can write, you can represent most things in three phases. You can represent them using a space phasor representation, and of course, this is the same. I mean, if you were given your space phasor, let's say, so if you have a vector like this, and you want to decompose it into your constituent components, you can say that each function fa of t, let's say, is equal to the real part of this vector or phasor. Fb of t is equal to the real part of the phasor or vector, whatever you want to call it. Let's call it a phasor, because vectors usually, phasors rotate in space, whereas vectors tend to be referring to some linear motion, or that's the convention that we usually use. And Fc of t is going to be the real component of this space phasor times e to the minus j4 pi over 3. So this is just how you, I mean, if you have three functions that look like this, you can represent them using this form here, and these here are your are how you decompose if you are in a position where you have the overall space phasor, but you want to get its individual components. So that's, again, this is a general mathematical concept. This is not unique to induction machines. So just something to be mindful of. Now, we can begin our analysis, or we can continue our analysis of the induction machine. So I want to start by defining a couple of terms. So I want to define sigma s, and I want to define sigma s as being ls over lm minus 1, and I want to define sigma r as being lr over lm minus 1, and this implies that ls is equal to 1 plus sigma s lm. Now this is going to be a fairly mathematical exercise, because what we're trying to do is we're going to model this these sets of equations, I guess, and using these equations we're going to derive a circuit model for the induction machine, and then we can use this circuit model for the purpose of control. So there's going to be a fair bit of derivation and mathematical rigor involved in this analysis that we're going to do here. So next what we're going to do is we're going to apply a change of variables, right? So we're going to say that lambda r, so let's say lambda r is equal to lambda r prime e to the minus j theta r, and we're going to say that Vr, the phasor, is equal to Vr prime, let's say, e to the minus j theta r, and we're going to have Ir, and this is Ir prime e to the minus j theta r, and these equations all imply the following. I mean, it's literally, I'm rearranging the equation, but I'm doing it here for the sake of completeness, so that if at any point we do use these equations, which we probably will, you will not be confused as to where they came from. So this is, again, for the sake of completeness, we're writing all of these equations, although it might be tedious and boring, I guess. It's better to be safe than to be sorry, I suppose. So we have these three equations, And now, using this change of variables and the definitions, well, let's start with the change of variables first. So equation 1 can be rewritten as following. And again, this is an exercise in order to establish a set of equations that we can use to model the induction machine. So I can essentially what I've done is I've applied this change of variables to this equation. Okay. Now I can do the same thing with 2. So equation 2 will give me an equation for lr prime. Sorry, lambda r prime, not lr prime. LMIS. Again, vectors. It's important to keep track of your vector signs when dealing with concepts like these. So we'll call this equation 4. Now if we apply our rotor and our stator leakage factors, the definitions, the sigmas that we used essentially, then what you get is you can rewrite 3, which is this equation up here that we just derived, as lambda s equals sigma s lm is plus lm is plus ir prime. And you can rewrite 4 just again substituting and then rearranging the equation. That's all we're doing here. So it's nothing fancy. It's just we're setting up the stage to match something that we are familiar with, and I'll explain what I mean by that later, because this probably doesn't look like anything we're familiar with. But when we get to the end, when we actually start to control things and we develop our control models, it'll make much more sense then. So these terms, this term here and this term here, so this is a leakage, we call it, and this we call a leakage. So this is the leakage in the stator winding, this one here, so let's say stator leakage, and this is the rotor leakage, right? So these two terms represent the leakages. Now, this is all we're going to do for now with these equations. What I will do is I can write these, since we have numbers so far, I can write this as 5 and I can write this as 6. Okay, now we're going to leave these equations alone for now, and we're going to go now, and we're also going to understand, we're going to say, okay, what else can we do here? Because we have, this is the relationship between the flux, or the flux linkages. Now, on the other hand, we have from Faraday's law, so let's say Faraday's law, and Faraday's law tells us that the time derivative of this flux linkage is equal to stator again for the stator voltage, or the stator winding, is equal to the stator voltage minus Rs and Is. And on the other hand, we have for the rotor side, you can do the exact same thing. So you have your rotor flux linkage is equal to Vr minus Rr Ir. Now, these two, so this Rs and this Rr, these are ohmic resistances. So this is the resistance of the winding, basically. So every winding, every wire has a resistance. The resistance of the windings that are involved in the motor or the induction machine are represented by Rs and Rr for the stator and the rotor windings, respectively. Now, I can write this, I can say this is 7, and let's call this 8. Okay. Now what I'm going to do is I'm going to apply the change of variables to equation 8. Okay. So if I do that, or I substitute those numbers in, or I essentially it's a substitution, right? So if I scroll up for a second, and you remember I said that VR is equal to VR, so this is the equation I'm looking at. VR is equal to VR prime e to the minus j theta r, and you can rewrite this as in that sense if you want. But so what I'm going to do is I'm going to rewrite it in terms of the prime. Okay, so I'm going to say that 8 can be rewritten as, just again substituting, the time derivative of lambda r prime e to the minus j theta r, back to time obviously, and this is Vr prime Again, making that substitution the change of variables that we made. And the whole purpose of the change of variables will become evident when we establish the model and we look at the method of control. For now, it all seems fairly arbitrary, but there is an objective and there is a method to the madness. So this is the equation you get, and then what you can do is you can simplify this equation a little bit, and if you do so, you'll find that this is the time derivative of r prime, should be at the top, of lambda r prime, and this is vr prime minus rr ir plus j omega r lambda r prime, and I'm going to call this 9, and I'm also going to define, because this omega r came out of nowhere, but I'm going to define omega r as being the time derivative of the phase, which we know to be true, right? So if you imagine for a second you're in a plane, and this is theta equals 0, whatever point you're at here, let's say, and this is some theta, as theta changes with respect to time, that's basically an angular velocity, right? So as you travel around this circle and the angle changes, that's an angular velocity. So this is one of the definitions of angular velocity. So we do that, and we can represent the equation in this way. And another thing to note is that this term here is referred to as the speed voltage. And the reason we refer to it as the speed voltage, because it's of voltage nature, and it is dependent on the speed. And again, you can go back to the theory related to the induction machine to find out more about the speed voltage, what it's caused by, how it's related to everything. For now, this is, if we get into those kind of details, these videos will get extremely long. And I have a feeling this one's already gotten fairly long for what I wanted it to be, but that's okay. So what do we have overall? Let's say overall we have some equations that we've just derived. Okay, now what are these equations? So we have the equation for lambda s, which is sigma s lm is, and on the other hand we had is plus ir prime. Okay, so this was one of the equations we had. Then we had another equation for the rotor flux, and we say this is lm is ir, both phasors, plus sigma r lm ir prime. Okay, and now we have these two equations we just derived here we had one from Faraday's law, and then we have one where we applied the change of variables. So from Faraday's law, we know that this is lambda s by dt, and this is also a phasor, and so this is vs minus rs is, and then the last one we have is the one we just got here, which is lambda r, not s, lambda r prime by dt, and this is vr minus rr ir plus j omega r lambda r. Now what's the purpose of all this? The purpose of all of this is that using these equations, you can now draw a circuit model, because these are physical parameters of a circuit. These are voltages, these are flux linkages, and so you can determine, or you can draw a model for the circuit, and you can use that model, which we will later on, for the purpose of analysis to understand how this machine works. So what does the circuit look like? Let's have a look. So the circuit's going to look something like this. So you have this resistance here, you're going to have some inductance here, you're going to have some inductance here, and I'll label them in a second, and then that will make a little bit more sense as to how we use the equations to get this. And then you have another winding here, you have another resistance here, you have some voltage here, and then you have a second set of terminals like this. So what's what? So this is RS, this is RR, so that means this side is the rotor side, and this side is the stator, obviously. You have, I'm going to call this LLS, I'm going to call this LLR, and I'll define what they are in a second. They're basically leakages, so we refer to them that way as opposed to carrying those sigma R, Lm all the time. And I'm going to define this, well, not going to define that, I'm going to just say that's Lm, which is the magnetizing inductance. And here we're going to have, this is our speed voltage. So this is J omega R lambda R. And we're going to have on this side, obviously, our stator voltage, Vs. And on this side, we're going to have our rotor voltage, Vr prime. And what else do we have? We have on this set of terminals here, we have, this is d lambda s by dt. And forgive me for a second while I just confirm something on my notes. Okay, and this one here, between here, is going to be d lambda r. And I guess we can also write our currents. So one current here would be IS, of course. And this current here is IR prime. And this current here we call IM. And IM is essentially the sum of the two. So why don't we define some stuff here? So I can define IM, phasor, as being equal to IS plus IR. I can define LLS as being equal to sigma S LM, and I can write LLR as being, or define it as sigma R LM. And again, these two terms here, so this and this, are referred to as the stator and the rotor leakage inductances, and IM is referred to as the magnetizing current. So I know this was a little intense because there was a lot of equations and such and a lot of substitutions, but it's necessary to establish a circuit model that we play with some equations, I guess. So what did we do? I mean, from the beginning, we went to, we I guess introduced a very simple model of the induction machine, physical model, I should say. We gave some equations, we made some manipulations, some substitutions, defined some terms along the way, and we arrived at this circuit model. And one thing I should also maybe mention, I guess it's an application note or practical note, is that in a squirrel cage motor, your rotor side is usually short. So this is for a squirrel cage. And they call it squirrel cage because I guess it looks something like what a squirrel cage would look like. Whatever a squirrel cage looks like. So, hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel. And we'll see you in the next one.